All right, good afternoon, and welcome to the Midterm 2 review session. I have some practice problems that one of the Calc 2 instructors put together. So my plan is to walk through these problems, and then we can also look at the practice exams that are posted on Canvas. I've got a list of all the topics from across the various exams that pertain to Midterm 2 in the new calendar for Calc 2. So we could work through that, and of course I'm happy to answer any and all questions. So if you have questions, put them in the chat, send them to me by email. I'd be happy to answer any of your questions, and I will be keeping my eye on my email as well. So let's go ahead and get started. This first problem here is about a solid of revolution. We have the region bounded by the curves y equals 3 and y equals the square root of x, and then the x-axis, or sorry, the y-axis, and we're going to revolve it around the y-axis. So there are formulas for solids of revolution. I think it's harder to remember the formulas and figure out which one applies than to just sort of think through each individual situation. So I'm looking at this this shape here, and we have two options. We could imagine splitting it up into rectangles this way, or into rectangles this way. If we do the vertical rectangles, we're going to end up having to evaluate or integrate a square root function, which is fine. The antiderivative of root x is 2/3 x to the 3/2. It's not that big of a deal. But if we integrated this way, we would only have to integrate a square function, because this is going to be rewritten as x equals y squared, and then we're going to be integrating with respect to y, so that'll be an integral of y squared. I think that's the easiest approach. So what I'm going to do is I'm going to draw in a little rectangle here. And I'm not just trying to find the area of this region, I'm trying to find the volume of the solid of revolution. So what I'm going to do is think about what happens when I rotate that circle, or sorry, that little rectangle around the y-axis. When I rotate that rectangle around the y-axis, it ends up looking like a disk. And let's see, so the area of the top face of that disk is a circle. So its area is going to be pi times the radius squared. What's the radius? Well, at a given y value, the radius goes from the y-axis out to the edge. So whatever this x value is, that's the radius of this disk. And that x value is y squared. So pi times y squared squared is the area of this circular face of this little cylindrical disc. And then the volume of a cylinder is the area of the top face times the height, which is dy. So that is the volume of this little cylindrical disc. And then to find the total volume of the shape, I just add up the volumes of all the discs as y ranges from 0 up to 3. So I'm integrating y to the 4th. Which gives me y to the 5th. I evaluate it from 0 to 3. And I'm going to get pi times 1/5 times 3 to the 5th minus 0. 3 to the 5th is 243. So the overall volume is 243 pi over 5. All right, we have another problem, another volume of a solid of revolution. I have the curve y equals 1 minus x squared. That's a parabola. It continues on like this, but we're just looking at one little portion of it. And we're going to rotate around the line x equals 2. So let's sketch that in. If I rotate around the line x equals 2, once again, I'm not worried about formulas. I'm just going to think about whether it seems easier to break the area down into vertical rectangles or horizontal rectangles. I think vertical rectangles are going to be easier because my function is 1 minus x squared. If I wanted to do horizontal rectangles, I would have to rewrite this as x equals the square root of 1 minus y, and then I would have to integrate something with a square root, which again, it's not that hard compared to many of the things you have been asked to integrate in this class. A square root function is not that bad, but I think it's going to be even easier to stick with a polynomial. Okay, so once again, I'm imagining a thin rectangle at an x value of x, and let's say it has a thickness dx, and then I want to think about what happens when I rotate this rectangle around the line x equals 2. Well, it's going to make a cylindrical shell. So I'll have another rotated copy of that rectangle over on the right side. Yeah, we've got a cylindrical shell. So we want to write down the volume of this little cylindrical shell. And the way that we do this is by imagining slicing the shell open and unwrapping it, and then it's a rectangle. It's a rectangle whose dimensions are the height and then the circumference. All right, when we unwrap it, the circumference of the original shell becomes the width of the rectangle. Let's see, so the circumference is 2 pi times the radius. What's the radius? Well, it's the distance from x equals 2 out to whatever this x value is. So it's going to be 2 minus x. Let's let's see. So 2 pi times that radius is the circumference, and then I need to multiply by the height, which is given by my function 1 minus x squared. And that is the sort of the area of the outer face of the cylindrical shell, but we also need to multiply by the thickness in order to get the volume. That's dx. And then all we have to do is add them all up, which means writing an integral sign, and the bounds on my x values are from 0 to 1. So this is the integral that we need to do. Let's expand out this binomial. Let's see. First, outside, inside, last. How did you determine your integral bounds? Yeah, so I look at what variable I'm using. I'm using x as my variable. And then I just look at the picture and ask, what are all the values of x that occur throughout this region? It starts at x equals 0. It ends at x equals 1. So the bounds are 0 to 1. In the previous problem, I was integrating with respect to y. And the shape had y values ranging from 0 up to 3. So my bounds were 0 to 3. Matthias, hi! Welcome to the Calc 2 review stream. How are you doing today, Matthias? Alright, so once we've written out the integral, we just need to find an antiderivative. I plug in 1. If I plug in 0, I do get 0. Make sure that you actually check that. This is a very common mistake, is to see a 0 here and think that you don't need to plug it in. That's true if you're integrating a polynomial. It's not true for all functions. But in this case, when I plug in 0, I get 0. So I have, let's see, I have some fractions I need to add together. I'm going to put these all over a common denominator of 12. Let's see, 3 over 12. (24 minus 4 is 20, minus 6 is 14, plus 3 is 17. So 17 pi over 6 is my answer. And the question similar to number 2, how would we account for the separated axis of rotation if we had to use the disk washer method instead of shell? Yeah, I'd be happy to walk through through this problem with the washer mesh method instead, and hopefully we'll get the same answer. And you also asked, how would you set up the integral if the axis was y equals -2? So y equals -2 would be down here. Well, yeah, then that would just be a totally different kind of question, because when you rotate that rectangle around, you get a washer. So it would be sort of similar to, well, here, let me just show you how to do this one using washers, which is what happens when you try to integrate with respect to y instead of with respect to x. Isn't that oh, x equals -2. Yeah, okay. Let's see. So if we did x equals -2 instead, it would look very similar. I think the only thing that would change is instead of 2 minus x, this would be -2 minus x. But that's it. That's the only thing that would have to change. It's not 2x squared once you multiply out the integral. Oh shoot, did I? Oh. Yeah, 2 times x squared is 2x squared. Good catch. So that makes that a 2. That makes this a 2. That makes this an 8. And that makes this a 13. Hopefully that's the only mistake. Yes, please point out any issues if you notice them. Can you always use the shell method if you rearrange for x or y? Yeah, exactly. In any solid of revolution problem, when you choose to integrate with respect to x or with respect to y, one of those is always going to be shells and the other one will be disks or washers. And I have not memorized like which one is which, like rotating around x equals something, integrating with respect to x. I guess that's what we just did, and we saw that was shells. But rotating around x equals something, integrating with respect to y is going to give us washers. Or it would be disks if the line we were rotating around touched the shape. But yeah, I haven't memorized which combination leads to which method of integration. I just draw the rectangle and then think about, like I actually draw this picture every time and then just think about rotating the shape and seeing what it makes. So if you have a preference for shells versus washers, you can choose the one that whichever method you like. I guess you'll always get shells if you make your thin rectangles that go in the direction that's parallel to the axis of rotation, and you'll get disks or washers if you pick the rectangles to go in the direction which is perpendicular to the axis of rotation. I always just go with whichever method makes the function simpler. Okay, so I think I've answered all the questions, but let's do the washer approach to this problem, which means integrating with respect to y. Okay, so when I rotate this rectangle, I'm going to get a washer. Its area is, well, it's a circle with a circle in the middle removed. So it's going to be pi times, well, it's the area of the outer circle, which is pi times the radius squared. The radius is the distance from 2 to 0. You can see that no matter what height I draw this rectangle at, the left end of it is always at x equals 0. So actually the outer radius is always 2. This is a distance of 2. And then the inner circle has a radius which goes from x equals 2 until it hits this curve. So we need to find the x value of that intersection given this y value. So I'll rearrange this as x equals the square root of 1 minus y. Oops, sorry, square root of 1 minus y. And I guess I panicked a little prematurely about having to integrate a square root function because that radius is getting squared anyway, so the square root goes away. This actually might be the easier integral to evaluate. Okay, so what I've just written down is the area of the outer circle minus the area of the inner circle, which gives us the area of the washer. And then to get its volume, I multiply by that thickness dy. And then to get the total volume of the shape, I add up all the integrals, or all the volumes of the washers, which means writing an integral sign, and my y values range from 0 up to 1. They're not... Oh, okay. This one, this x value is labeled. The y value wasn't labeled here, but you have an equation. Just plug in x equals 0, and you get 1 minus 0. So the y value is 1. Okay, I have a constant factor of pi that I can pull outside of the integral, and I'm left with 4 minus 1 minus y, which, when I distribute the minus sign, becomes 4 minus 1 plus y, which is 3 minus y. Sorry, 3 plus y. And my antiderivative will be 3y plus 1/2 y squared. I evaluate from 0 to 1. I'll get pi times 3 plus 1/2, which is pi times... that's 7 pi over 6. Sorry, 7 pi over 2. And now we have a slight problem, which is that I got a completely different answer from the other method. So if anyone notices the mistake, please let me know. Otherwise, I'm going to try to figure out if I did one of these integrals wrong. Help me out, chat. Okay, I'm doubting this one a little bit more. 2 pi times the radius times the height minus x minus 2x squared plus x cubed. 2x minus 2/3 x cubed minus 1/2 x squared plus 1/4 x to the 4th. Shell method is right. The inner radius. Oh, yeah, sorry. Yeah, of course. I'm supposed to do 2 minus the x value. I just wrote down the x value. Thank you. Unfortunately, that does kind of mess up the whole thing. Okay, so maybe I was right to be wary of this one. We will have to integrate a square root because the radius of the inner circle in the washer is 2 minus root 1 minus y. Thank you. Okay. So when I square that out, I'll get 4 minus 4 times root 1 minus y plus 1 minus y. I just FOILed this out. Let me pull the pi outside the integral. These 4's cancel, which is nice. And I end up with plus 4 root 1 minus y plus 1 minus y. Oh, sorry, minus 1 plus y. I'm still distributing the minus sign. So when we look for an antiderivative for root 1 minus y, that 1/2 exponent gets bumped up to a 3/2, and 8/3 is the thing I need to put in front. So when I multiply 3/2 and 8/3, I get 4. Okay, now when I plug in 1, I get 0 minus 1 plus 1/2. And then when I plug in 0, this gives me 8/3. And that's 0, and that's 0. Somehow I've still messed this up, because this is negative. Yeah, sorry. There's a minus sign here. Because of the chain rule. Because there's a minus y inside. Okay. So this is 1/2 minus 1 plus 8/3. Which is pi times, let's put everything over 6. That's 3 over 6 minus 6 over 6 plus 16 over 6. 16 minus 6 is 10 plus 3 is 13. So we get 13 pi over 6. Finally, that agrees with the answer from the other method. Okay, we got there eventually. But I guess this just goes to show that my idea to integrate with respect to x actually was the easier choice. Because the function is a polynomial. When you integrate with respect to y, you end up with a square root. Okay, there we go. Any more questions about volumes of revolution before we move on to work problems? Alright, this next question asks, a force of 10 pounds is required to hold a spring stretched 4 inches beyond its natural length. How much work is done in stretching it from its natural length to 6 inches beyond its natural length? Okay, so Hooke's law tells us that the force is proportional to the distance. And I guess we usually put a minus sign in there to indicate that the force is opposite the direction that the spring is being pulled. And an x here means how far the spring has been stretched beyond its natural length. So they tell us that 10 pounds is needed to stretch the spring 4 inches beyond its natural length, which means that k is, you know what, let me just erase the minus sign. We're not worrying about direction here, or at least, we can interpret the problem appropriately. We don't need to put the minus signs into the equation. The constant here, though, is 10 divided by 4, or 5/2 pounds per inch. And then the work is always an integral of force times distance in this case, our force is k times x, and we are stretching the spring from its natural length to 6 inches beyond that. So we integrate from 0 to 6. The antiderivative is 1/2 kx squared. Let's see. And now we substitute in. K was 5/2 pounds per inch. And I'm substituting in, I guess I should probably actually include units. But I get 5/4 pounds per inch times 36 inches squared, which is 45 pound inches. And pound times inch is a unit of energy, so this makes sense. All right, next one. A 600-foot cable is 100 feet long and hangs vertically from the top of a tall building. How much work is required to lift the cable to the top of the building? Okay, so let me sketch this cable. Let's see, here's the building. Let's draw some windows. Okay. The building only has windows toward the top for some reason. But we have our cable, which is 100 feet long. And we're going to look at just some little portion of the cable. Let's say that it's at a height of y. And I guess we might as well set up our coordinate system so y equals 0 is at the bottom of the cable and y equals 100 is at the top. And let's say that the length of the cable is dy. Once again, work is force times distance. And the point is that it's a lot easier to think about just one chunk of the rope at a time, and then I add all the results together with an integral. So the force acting on this little piece of the cable is its weight Remember, weight means gravitational force. Well, weight is a force. If we were given the mass of the cable instead of the weight, to find the weight of the piece, which is the gravitational force, we would have to do the mass of the piece times the gravitational constant, lowercase g. But we're given the weight, I believe, right? They told us the cable is 600 pounds, exactly. So that the unit of pounds already has the strength of the gravitational force on Earth built into it. Okay, and the distance, well, let's simplify the weight first, and then think about the distance. What's the weight of this cable, or this little piece of the cable? Well, the weight of the whole cable, is 600 pounds. But that's the whole 100-foot long cable. We just have a piece that's dy units long. So the fraction of the cable that we're looking at is dy over 100 feet. And if I multiply that fraction of the cable by the total weight of 600 pounds, that tells me the weight of this small piece. For example, if dy was, if you substituted 0 for that, you have no cable, so the weight would be 0. If you plug in 100 feet here for dy, you'd get 100 feet over 100 feet, which is 1, so you'd get that full weight of 600 pounds. If you took half the cable, so dy was 50 feet, you get 1/2 times 600 pounds, which is 300 pounds. Yeah, another way to think about this is this 600 pounds over 100 feet. That simplifies to 600 pounds per feet. It's telling you every foot of the cable weighs 6 pounds. So you multiply that density by the length, and that gives you the weight of that portion of the cable. Okay, so that's the weight, and then the distance how far do we need to move the cable to lift it up to the top of the building? Well, it's whatever this distance is. It's how far away, or how far the height is below 100 feet. In other words, it's 100 minus y. So that's the work required to lift this small piece of the cable up to the top. To find the work for the total, for the entire cable, we just integrate that. And y is going from 0 feet up to 100 feet. That is the range of y values that span the length of this cable. So as I mentioned, this constant simplifies to 6 pounds per feet. And then I have 100 feet minus y dy. An antiderivative of 100 minus y is going to be 100y minus 1/2 y squared. When I plug in 0, I do get 0. So when I plug in 100, I get 10,000 feet squared minus 1/2 of 10,000. And again, that's feet squared. Half of 10,000 is 5,000. 10,000 minus 5,000 is 5,000. And when I multiply pounds per feet by feet squared, one of these units of feet cancels out with that one, and I'm left with, let's see, 5 times 6 is 30, and then I have 2 and 3 more zeros. So 1, 2, 3, 4, 5. That comes out to 3 million pound-feet, which once again is a unit of energy. Okay, so that's the chain problem. Now, let's move on to everyone's favorite kind of work problem, which is the tank. We have a tank full of water. We want to find how much work is needed to empty the tank. To pump it all out of this spout, which is 2 meters above the top of the tank. Okay, so it's the same strategy as with the chain. The geometry just gets a little bit more involved. So let's look at one or slab of water in this tank. And as always, the work is equal to the force, which in this case is the weight, times the distance. The weight is going to be volume times density. Let's see, the volume of a rectangular prism is length times width times height. So I've got 21 meters times whatever this is. This is going to be the hard side to figure out, and then that's dy. So 21 meters times the width times dy. Let me fill in the rest, and then we'll come back and think about the width, because that's the hardest part of this. But that was the volume. And the density, we're told, is 1,000 kilograms per meter cubed. Oh, this time we do need to include the gravitational constant g. Okay. So the weight is the mass times g. And the mass is the volume times the density. Let's just go ahead and write out what g is. It's 9.8. Oops. Oh, sorry, you can't really see this on the screen, can you? Okay, I think that fits on the screen now. Great. Okay. G is 9.8 meters per second squared. And we still need to find the distance. Oh, but the distance, that one is not so bad. How far is it from here up to the top of the spout? Let's use a coordinate system where this is y equals 0, and then that's y equals 5 meters, because the tank is 5 meters tall, and then the spout is another 2 meters above that, so this will be y equals 7 meters. So if this is at some height of y, then the distance that we have to lift this slab of water vertically from its current location of y up to 7 meters is 7 meters minus y. So the distance is (7 meters minus y). Do we need to include units through the whole process to get full points? I can't answer questions about how things will be graded because I'm not an instructor for Calc 2 here. My recollection, my general feeling is probably you don't need to, as long as you have the right units at the end. I personally just find it helpful to include units throughout, so I don't make any mistakes. Can we first move the whole thing 2 meters up? To ignore the spout? Yeah. You could absolutely do that. So that's sort of thinking of this in 2 stages. One of it is to get all of the water up to the height of the top of the tank, and then all of the water goes up a constant distance of 2 meters. That would be fine too. So you'd be adding on the total weight of the water times a distance of 2 meters just for that portion. In practice, it might not be easier to do that because you'd still need to do that calculation, which involves finding the weight. But yeah, that would be one approach. Okay, so we still need to find the width here. So the width increases from 0 at the bottom of the tank to 5 meters at the top of the tank as the height increases from 0 to 5. Actually, that means the width is equal to the height. The point is that these 2 triangles won't let me draw. It's snapping it to the grid in an annoying way. This triangle is similar to this triangle. And when you have similar triangles, the ratios of the corresponding sides are equal. So in the big triangle, I see that the top side is 5 meters, and okay, I guess if I really wanted to do this carefully, I would draw this in. But the top is 5 meters. When the height is 5 meters, that means that for the little triangle, which is similar to the big one, the top edge is going to have the same length as the height. So the width is y. So if we gather all of the constants out front, I've got 21 meters times 1,000 kilograms per meter cubed times 9.8 meters per second squared. And what am I left with? I have y and 7 meters minus y dy. So the total work is the integral from 0 to 5 meters, because I'm looking at the full range of y values where I have water. And I guess the point is that these constants can come outside of the integral. And I'd be integrating y times 7 meters minus y. Which is 7 meters times y minus, whoops, I did not mean to square that, minus y squared. It would find an antiderivative, which would be 7 meters over 2 times y squared minus 1/3 y cubed. And we'd substitute in the 5 meters, multiply everything out. If this is on an exam, my recollection is that usually you would just be asked to write out an integral evaluating the quantity. You know, if you don't have a calculator to use, we're not going to ask you to multiply 21 times 9.8. But I am curious to think about the units. The units of this, when I'm plugging in something with units of meters, it's getting cubed. Here it's getting squared and multiplied by another quantity in meters. So the units of this thing are meters cubed. When I multiply that with all the units here, I guess the meters cubed cancel. I'm left with meters times kilograms times meters per second squared, which is a unit of energy. That's a joule. So it all works out. Yeah, probably you would be fine not being quite so careful with units throughout and just making sure to get the correct units at the end. And in this case, the units are joules. All right, those are the work problems. Questions about any of the work problems before we move on to the next application of integration, which is center of mass. Alright, oh, what's the diameter of the spout? It doesn't matter. And we're not told what it is. The point is that work is only done when you move perpendicular to the force. So it doesn't take any energy to move an object horizontally, or at least you don't need to do work against the gravitational force. All that matters when you're considering gravitational work is moving up or down. So the details of how the water gets up to this height of 7 meters don't matter. All that matters is, you know, how far all of these little pieces have to go to get up to a height of 7 meters. Okay, we've been going for a little over an hour now, or I guess almost exactly an hour. So why don't we take a short break? I'll give you a chance to think of any questions you have about the stuff we've done so far, volumes of revolution, work problems. If you think of any questions, put them in the chat, email them to me, and then let's start up again at 4:10. Alright, so we'll come back at 4:10, which is in about 6 minutes. I will run some ads during the break, because if I run enough ads, it keeps people from seeing ads when they join the stream. I'm trying to, I can't shut off ads completely, apparently, but I'm just trying to make sure that the ads don't interrupt me when I'm talking. That's my goal here. All right, so see you in like 6 minutes. Okay, it's 4:10, so we're back. Let me just get the iPad up here again. All right. I don't see any questions in the chat about these work problems, so let's move on to center of mass. All right, we're going to find the center of mass of this lamina, which has the equation y equals 1/2 x squared as the top boundary. And we're going from x equals 0 to x equals 2. Okay, so I need to compute the total mass and then the moments with respect to x and y. So let's find the total mass first. There are formulas, but I don't memorize these formulas. It's the same as with volumes of revolution. I find it easier to just draw one of these little rectangles and then just sort of think about that piece and add up all of the pieces. Okay, so the mass of this little piece is its area times the constant density of rho. Mass is area times density. So the area of the rectangle is width times height. The width is dx. The height is this y value, which comes from the equation. So it's 1/2 x squared. Right, area is width times height. And the density is rho. So the total mass is that thing. It's just the mass of the little rectangle, but we add up the masses of all the rectangles. So I add an integral sign, and my x values range from 0 to 2. Pull out the constant 1/2 rho. I'm integrating x squared, which gives me 1/3 x cubed. We're integrating from 0 to 2. I plug in 2. When I plug in 0, I get 0. So I get 1/2 rho times 8/3, which is 8. Sorry, that simplifies. Actually, that's 4/3 times rho. Will there be a replay? So the recording will be available afterward to watch, if that's what you mean. So we found the total mass. Now I need to find the moments for x and y. I always get confused by the notation. Like for the x coordinate of the center of mass, I think you use the thing that's called my. But the way I just think about this is, again, I think about one little rectangle at a time, and I think, what does that contribute to the average? For x. And I'll go ahead and write the integral from 0 to 2 right away this time. But what is this little piece contributing? It's contributing its mass times its x value. Mass times the x value. Maybe I'll even write dm to indicate the mass of this little rectangle. So mass times x value. We already talked about what the mass is. It's 1/2. Wait, sorry. Yeah, this was the mass of that little piece. 1/2 times rho times x squared times dx. 1/2 times rho times x squared dx. So this is identical to the integral that we did before, except that there's this extra factor of x. Oops. So we end up integrating x cubed instead of just x squared. Oh, sorry. And one other little detail. I need to divide by the total mass. Alright, so I get 1/4 times 3. That was supposed to be a 2. Why did I change that to a 3? Weird. Maybe it was because I was talking about how the only difference between this and the previous integral was that the x squared ended up being an x cubed this time, and maybe I changed another 2 to a 3 that I wasn't supposed to. So 1/4 times 16 is 4. And let me remind myself what the total mass was. It was 4/3 rho. So I have the reciprocal of 4/3 rho. That's 3 over 4 rho times 1/2 rho times 4. A lot of stuff cancels out here, which is nice. The rows cancel, which of course they have to. The answer shouldn't depend on the density. The 4's cancel, and I'm just left with 3/2, which is 1.5. So right about here. Does that make sense as the center of mass? Oops, sorry, that's not right there, that's right here. Does this make sense? That looks reasonable to me. Divide by the total mass. Yeah, thank you, D-Boss. I almost forgot about that. And then the y-coordinate, or the y-coordinate of the center of mass. Once again, we do need to divide by the total mass. This is the one that has the weirder formula, but again, I don't memorize the formulas for these things. Let me just show you how I think about this, because I really do think it's not too hard to think about it if you just analyze one piece at a time. So I have this rectangle here. The contribution of this rectangle toward the average y-coordinate across the whole mass is the mass of this piece times the y-coordinate on average of this piece. It's the average y-coordinate of this piece. But this is just a rectangle. The average y-coordinate of this little rectangle is just right in the middle. So this is, if I call this function f of x, the average y-coordinate for that rectangle is f of x over 2. Okay, so mass, the little mass, dm times f of x over 2. And I really just want to highlight that these formulas, even though they look very different and it might be hard to remember them, they're really the same formula. In both cases, you're dividing by the total mass, you're integrating across the region, which means adding up something for all the rectangles, and then you're doing the mass of that little rectangle times, well, this is the part that differs. When you're trying to find the average, or the x-coordinate of center of mass, you take the average x value for the rectangle. But the point of doing the tiny rectangle is that it's so small we can pretend the whole thing is just at x. Whereas to find the y-coordinate of the center of mass, we look at the average y-coordinate for the rectangle, which is half of the height of the rectangle. Okay, so this is going to be 1 over m times the integral from 0 to 2 of 1/2 times, well, f of x is 1/2 x squared, right? Yep, 1/2 x squared. And once again, dm is 1/2 x squared dx times rho. So that dm piece is exactly the same as it was before. Okay, if I pull all the constants out, I think I'm going to get, see, I have 1/2, 1/2, 1/2 in a row. So that's 1/8 times rho. And I'm integrating x to the 4th this time. So I'll get 1/5 x to the 5th. I integrate from 0 to 2. It gives me rho over 8m times 1/5 times 2 to the 5th, which is 32. Again, I should make sure that, I've thought about plugging in 0, but that gives me 0. 32 over 8 is 4, so I get 4 rho over 5m. So I've got 4 rho over 5, and then I have this reciprocal of m. The reciprocal of m would be 3 over 4 rho. This is very nice. The 4 rho's cancel out, and I'm left with 3/5. Let's see, does that make sense? When I plug in x equals 2, I get 2. So that's 2, this is 1. So we're saying the average y-coordinate is right about here at 0.6. I think I believe that. That looks reasonable to me. So the center of mass overall is right about here at 1.5 comma 0.6. Okay, questions. Is f of x squared for this one? Yeah, great question, Rev. Yes. I took a slightly different approach where I didn't just write down the formulas. I sort of worked out all the pieces. So this piece has an f of x that's coming from the average y-coordinate of the rectangle. And then the mass of the little rectangle also has an f of x in it. So here you see an f of x, and here you see another f of x. So there really is an f of x squared here. So I guess the formula is you divide by the total mass and you integrate 1/2 times f of x squared times rho. Any other questions about center of mass? All right, I'm going to move on. If anyone thinks of any questions later, go ahead and ask. But for now, we're going to move on to parameterization. So the next problem asks us to parameterize a circle, the unit circle, in 2 different ways. So take a moment to think about how you would do this. Okay, so one way I would go about this is to use an angle theta, and then the coordinates of the point here are cosine of theta, sine of theta. So I guess my parameterization is x equals cosine theta, and y equals sine theta, and theta ranges between, let's say, 0 and 2 pi. So this parameterization goes around the unit circle once at constant speed in the counterclockwise direction. Another parameterization could be the same x-coordinate, cosine theta, but y could be minus sine of theta. The difference here is that, well, the first parameterization goes counterclockwise around the circle, the second parameterization goes clockwise around the circle. So that's one change I could make. I could also do things like putting a constant multiple inside there, like make it 2 theta, and then I'd only need to go up to pi on the angle. That would go around twice as fast. I could like swap the sines and cosines, which would, if I just swapped the sines and cosines, switching x and y reflects across the line y equals x. So instead of starting here going that way, it would start up here going this way. So there are many, many different ways you could parameterize this. I could, instead of doing theta, I could do theta plus, I don't know, like pi over 4. I could add on a constant term, and that would start at a different point and go all the way around. So you could get as creative as you like here. Find the equation of the tangent line to the parametric curve given by these equations. Oh, at t equals pi over 2. Okay, great. So I would always ask my Calc 1 students last semester, I guess for the past 5 semesters when I taught Calc 1, what 2 things do you need to find the equation of a line? You need a point on the line, and you need the slope of the line. So the point is easy. We just plug in pi over 2 for t to find the x and y coordinates. So at time pi over 2, the x coordinate is 2 times the cosine of 3 times pi over 2 minus 4 times the sine of 3 times pi over 2. the cosine of 3 pi over 2 is 0, and the sine of 3 pi over 2 is negative 1, so this comes out to 4. And the y-coordinate is obtained by plugging pi over 2 in for t to the y equation, which is 3 times the tangent of 6t. Six times pi over 2 is 3 pi. The tangent of 3 pi is 0. So at time pi over 2, this curve passes through the point 4, 0. We also need to find the slope of the tangent line, which is given by the derivative. And the way that we find the derivative with a parameterization is, well, we're looking for dy dx. And we find that by computing dy dt and dividing it by dx dt. You can kind of think of this as canceling out the t's to leave you with dy dx, but remember, these dt's aren't like really quantities that you can algebraically manipulate. So the real reason that this is correct is that it's the chain rule. This is the chain rule. We just brought one of the quantities over to the other side. Okay, so let's compute dy dt. That's the derivative of 3 times the tangent of 6t. That's going to give us 3 times the secant squared of 6t times 6. It's because of the chain rule that I need to multiply by the 6. We are multiplying by the derivative of that inside factor of 6t. And then let's go ahead and evaluate this at pi over 2. Since I need to know the slope of the tangent line specifically at time pi over 2, this angle of 3 pi, well, secant squared means take the cosine and then take the reciprocal and then square it. The cosine of 3 pi is negative 1. The reciprocal of negative 1 is still negative 1, but then I square it, it becomes positive 1. So dy dt is 18. For dx dt, I'm differentiating, let's see, 2 cosine of 3t minus 4 sine of 3t that will give me minus 6 sine of 3t minus 12 cosine of 3t. And at t equals pi over 2, this is going to become minus 6 times the sine of 3 pi over 2 minus 12 times the cosine of 3 pi over 2 sine of sine of 3 pi over 2 is negative 1. Cosine of 3 pi over 2 is 0. This comes out to positive 6. So let's put this together. If dy dt is 18 and dx dt is 6, that means that dy dx is 18 over 6, which is 3. So the slope of the tangent line is 3, and we already said the tangent line passes through the point 4, 0. So the equation is y minus, let me write this. Point is 4, 0, and the slope is 3. So point slope form, y minus 0 is equal to m times x minus x0. And I could simplify that to y equals 3x minus 12. Okay, we've got another parameterization question. We want to set up an integral that represents the length of the part of the parametric curve shown in the graph. Okay, so I've got equations for x and y, and t is going from 0 to 4 pi. We want to find the length of this. Okay, length is, and again, there's a formula, but if you just break things down into pieces, you don't really need to memorize a lot of formulas in this class. So if I look at one little portion of the curve, I've got dx, dy, and I'll call the hypotenuse ds. The Pythagorean theorem says that ds squared is dx squared plus dy squared. And I'm really interested in the quantity ds. That's the length of this little piece of the curve. I just want to add that up for the whole curve. ds is the square root of dx squared plus dy squared. And I have a parameterization with a parameter t. So I want to do everything in terms of t. I can divide by t squared on the inside, as long as I also multiply by t squared, or dt squared, but then the square root is going to reduce that to just dt. Okay, so if you just want to memorize the formula, that is totally fine. I just want to show you how the formula just comes about by analyzing one little piece, right? All of the applications of integration are just, right, the moral of the story is always, it's easier if you just think about one little piece at a time. And in this case, it's just the Pythagorean theorem. So the total length of the curve is the integral. I just add up all the little lengths along the curve. So I'm integrating the square root of dx dt squared plus dy dt squared with respect to t, and t I believe is going from 0 to 4 pi. Okay, so let's find dx dt and dy dt. The derivative of t minus 2 sine t is 1 minus 2 cosine of t. And the derivative of 1 minus 2 cosine of t is 0 plus 2 sine of t. All right, so I'm integrating 1 minus 2 cosine of t squared plus 2 sine of t squared. Hopefully some trig identities will make this simpler to integrate. That's the thing about these arc length formulas, is for most functions they come out very messy. Alright, but if I FOIL this out, I get 1 minus 4 cosine of t plus 4 cosine squared t, and then 2 sine of t squared is 4 sine squared of t. Okay, that simplifies at least. Because cosine squared t plus sine squared t is 1. So I'm supposed to integrate the square root of 5 minus 4 cosine of t. Whoops. All of these 4s should be 4 pi's. Did I do everything right here? I'm worried that that's a hard integral. Oh yeah, that's an elliptic integral of the second kind. This is not an integral that you could do by hand. Okay, but we set up the integral. Oh, we were we were only even asked to set up an integral. Okay, so we were not going to be able to do this. Okay, let's move on to polar curves. Graph the polar curves r equals 2 cosine of 2 theta and r equals 2 cosine of 3 theta. Let's see. Okay, so cosine goes from 1 down to -1 back up to 1 as the angle goes from 0 to 2 pi, but because we have a 2 theta, that's all happening as the angle goes from 0 to pi. All right, so let me try to graph this first one. There's not really a lot of space in this document to do this. Okay, so when theta is 0, the radius is 1, and then when as theta increases to, let's see, cosine goes down to 0 at pi over 2, but that's actually going to happen at pi over 4 now. So as theta increases from 0 to pi over 2, oh, sorry. As theta increases from 0 to pi over 4, the cosine is going to decrease to 0. And then, what happens next? Cosine continues decreasing to -1. That's going to look like this. We're now at the point pi over 2 with a radius of -1. So we're actually down here at 0, -1. And if you keep thinking about what happens as theta increases, it's going to make this sort of shape. And if we replace the 2 theta with a 3 theta, we end up with a different number of petals on this shape. Okay, graph the polar coordinates, or polar curves. Here, I'm not going to graph these, but I'll show you how I would go about this. I'm just going to do a little bit of algebra to rewrite these in Cartesian coordinates. So if I have r as 2 plus cosine theta, I see that cosine theta, and that makes me think of y. Or sorry, x. If I multiply everything by r, well, this becomes x. Now I'm concerned about this. Maybe that's fine. And then r squared is x squared plus y squared. This looks overly complicated. Maybe it's not meant to have a simple a simple equation in Cartesian coordinates. No, it should. I'm doing something wrong here. This is supposed to be just a circle. What about the 2 that's multiplied by cosine of 2 theta? Right. The problem before. Oh, sorry. Okay. Oh, I was kind of ignoring that, but multiplying r by a constant factor is just going to stretch everything out. So this, instead of going from -1 to 1, it goes from -2 to 2. Good catch. Yeah, just it rescales everything, but it doesn't really change the shape. Okay, let me come back to this one because something's not clicking for me right now. This one should be fairly easy to analyze, though. If I multiply both sides by r, and again, I want to do that because when I see cosine theta, I'm thinking that's sort of like an x-coordinate, where it would be if I had a factor of r. So r squared is x squared plus y squared, and then r cosine theta is x. So I have x squared minus 3x plus y squared equals 0. Yeah, okay, okay. And then to really see that this is a circle, I want to complete the square. So I'm going to add in, oops. I'm going to add in 9/4 to both sides. And the reason I want to do that is because then I can factor this as x minus 3/2 squared. So I came up with the 9/4 by dividing 3 in half to get 3/2 and then squaring it. And I guess I could write that 9/4 as 3/2 squared. So this is a circle centered at 3/2. 3/2 comma 0, and it has a radius. That's not a great circle. It has a radius of 3/2. Oh, okay. So this 2 plus cosine theta, this actually is. It's not a circle. It's something a little more complicated. You could sketch it by sort of just thinking about different values of theta, some nice angles, and then sketching them on a graph. But maybe, yeah. We've talked about some examples of polar curves. I feel like it's maybe time to move on. If anyone wants, I'd be happy to talk about this one too. Find an equation of the tangent line to the polar curve r equals 2 cosine theta at theta equals pi over 3. Okay. We've already actually done a similar sort of problem with parameterizations, finding dy dt, or finding the tangent line. Sorry, dy dx. So it's a similar process here. I'm looking for dy dx. And once again, I can find this by computing dy d theta and dx d theta. Now we don't have y and x, but we can come up with them. So we know that r is 2 cosine theta. Well, y is r sine theta. Which means y is 2 cosine theta. That's the r times sine theta. So dy d theta is the derivative of 2 sine theta cosine theta. You could use the product rule. I see a shortcut, which is, I recognize a trig identity here. 2 sine theta cosine theta is the sine of 2 theta. So this is going to be 2 cosine 2 theta. And then we're interested in the point pi over 3. So let me plug in theta equals pi over 3. And that's going to give me 2 cosine of 2 pi over 3. Which is minus 1/2. So I get negative 1. That was dy d theta. I also need dx d theta. So x is our cosine of theta, which is 2 cosine theta times cosine theta. So dx d theta is the derivative of 2 cosine squared theta, which is 4 cosine theta times minus sine theta. And again, I'm going to use that trig identity just to simplify this a bit. This is minus 2. It's not necessary. You could plug in theta for both cosine and sine. Sorry, that's 2 sine of 2 theta. Minus 2 sine of 2 theta. And when theta is pi over 3, this is going to come out to minus 2 times the sine of 2 pi over 3. Sine of 2 pi over 3 is root 3 over 2. So overall, this is minus root 3. And that means, oh, sorry, that's off the screen again. That means that dy dx is dy d theta, which was negative 1, over dx d theta, which is minus root 3. So it comes out to 1 over root 3. And we were asked to find an equation of the tangent line. So I should also find the y and x coordinates. Y is, we worked out y is sine of 2 theta. That's root 3 over 2. And x, we found that x was 2 cosine squared theta. And theta is pi over 3. So that's 2 times 1/2 squared. Cosine of pi over 3 is 1/2. So this comes out to 1/2. Okay. So the tangent line, I guess, would be y minus root 3 over 2 equals m, which was 1 over root 3, times x minus 1/2. I want to check if this is right. And to do that, you know, and checking answers like this is something you should get in the habit of for, you know, homework. Of course, you can't do this on an exam, but I can go over to Desmos and I can graph this equation. It was r equals 2 cosine of theta. That's a circle. And we were looking at the point let's see, sorry, the x and y coordinates were 1/2 and √3/2. Okay, so the point is in fact on the circle. That's reassuring. And the equation I came up with was y minus square root 3 over 2 equals 1 over the square root of 3 times x minus 1/2. And that is in fact the tangent line. All right, we did it. Okay, what is left here? We've got another polar coordinate or a polar curve problem. Oh, we were given graphs. Okay. I didn't notice that we were given these two graphs here. So this asks us to identify the two curves. So which one is 3 cosine theta? That would be this one. We carefully worked out the equation r equals 2 cosine of theta. We saw that it was a circle with the left endpoint at whose left side is touching the origin. Changing that 2 to a 3 is going to give us the same shape, essentially. It just makes the circle a little bit bigger. Instead of going from 0 to 2, it goes from 0 to 3. So the other one must be r equals 3 minus 3 cosine theta. Next, they ask us to find the area of the region that lies inside this and outside of the other one. So that's this. So they want us to find this area. To do that, I would need to find these angles because I'm going to set up an integral with respect to theta. Right, so my values of theta are going to start out down at this negative angle and then increase up to whatever this positive angle is. Now to find those angles, I need to set the curves equal to each other and find the points of intersection. So that means setting 3 cosine theta equal to 3 minus 3 cosine theta. If I add 3 cosine theta to both sides, I get 6 cosine theta equals 3, or cosine theta equals 1/2. This happens at minus pi over 3 and pi over 3. So the area is going to be an integral from minus pi over 3 to pi over 3 And the quantity that we integrate is 1/2 r squared why does it say 1/2 r squared d theta? This feels wrong to me. Is that right? Can people confirm if this is the correct formula? Yeah. Yep, that's right. Okay. And what's r? I have two options here. But the point is that at any given theta, I guess this is slightly trickier because I just want this piece. So I don't just do 1/2 r squared. I do the outer r squared and I subtract the inner radius. So the outer one is 3 cosine theta. And the inner one is 3 minus 3 cosine theta. When I square these things, I get 9 cosine squared theta minus 9 minus 18 cosine theta plus 9 cosine squared theta. Fortunately, we don't end up having to integrate a cosine squared theta. Those are going to cancel out. What I do have to integrate is 18 cosine theta minus 9. And I will leave it to you to evaluate this definite integral. The last thing they asked about in this question was integrating or finding the area of the region that lies inside this, I think that's called a cardioid, and outside the circle. So it's all this area out here. They're asking if we can do that with a single integral or not. The problem is if I integrate from pi over 3 all the way around to, I guess that would be 5 pi over 3, it's going to include this area. So really what I need to do is I can integrate this cardioid from pi over 3 to 5 pi over 3, but I also then need to integrate, I need to find this area and subtract. And I could do that by, well, I could find this area by integrating the circle, the r equals 3 cosine theta. I could integrate that from pi over 3 up to pi over 2. So in practice what I would do is I would integrate the cardioid from pi over 3 up to pi just to get the top half. But remember, that also includes this little wedge. And then I would integrate this one. I would integrate the circle just from pi over 3 up to pi over 2 to get the area of this wedge, and I would subtract that, and then I would double the whole thing to get the area down here as well. So that's how I would go about this. Okay. There's one section left on sequences and series. But again, we've been talking for like another hour, so why don't we take another short break? And then we'll do the sequences and series questions. During the break, if anyone thinks of any questions, feel free to send them in the chat or to my email. But let's take a short break, and again, I'll have some ads run during the break so that folks joining the stream don't see any ads. My hope here is that no one's seen an ad while I've been talking. If that's happened to you, let me know so I can try to figure out how to avoid that. All right, 5-minute break. I'll see you back at 5:17-ish. All right, we're back to talk about sequences and series. But first, there was a question in the chat about why there's a 1/2 in the formula. So the reason is that we're looking at this little triangular wedge here. So let me draw a bigger copy of that triangle, and you might object, it's not really a triangle because the outer portion there is curved, but when we're dealing with an infinitesimally small little sector here, it doesn't matter. So this is essentially R, this is R, and again, they're not quite the same. I guess if we're being careful, we could call that R plus dr, but the point is dr is tiny. So I can just treat both sides as R, and then we have some angle theta. And where the 1/2 comes in is that there's a formula, which is the area of a triangle. If you have any triangle, and if you know 2 of the side lengths and the angle between, the area is 1/2 AB sine of theta. If you do this with like a right triangle, this becomes the familiar formula 1/2 base height, because the sine of 90 degrees would be 1. But yeah, this is just a geometric formula. This is exactly true for any triangle. 1/2 times 2 side lengths times the sine of the angle in between. So here, the little area is it's 1/2 times these 2 side lengths, both of which are R, times the sine of that. I guess I should call this d theta. Okay, this is not, again, this is maybe not great to write sine of d theta, but the point is that when an angle is small, the sine is approximately equal to the angle. So I can replace the sine of d theta with just d theta. That's where the area form, that r squared, and the 1/2 come from. It's from this formula for the area of a triangle. Okay, so sequences. We're going to determine whether these sequences converge or diverge. The first sequence here is n to the 4th over n cubed minus 2n. But when n is large, this minus 2n doesn't really matter, so this is approximately n cubed, or n to the 4th over n cubed, which is n. So this sequence diverges to infinity. The second sequence, e to the minus 1 over root n, well, when n is big, the square root of n is still big. Minus 1 over a big number is a very small negative number. So this minus 1 over root n is approaching 0 as n approaches infinity. So overall, the sequence is approaching e to the 0, which is 1. For part C, this negative 1 to the n is toggling the sequence terms between positive and negative, but that 2 root n in the denominator is getting bigger and bigger. So overall, the quantities are getting smaller and smaller. They're flipping back and forth between positive and negative, but they're getting closer and closer to 0. And then for this last one, let me rewrite this in what might be a more helpful form, cosine of n pi over 2 to the n. This cosine of n pi bounces around between 1 and negative 1, but we're dividing it by terms that are growing exponentially. This is approaching 0. Okay, next question. What's the difference between a sequence and a series? In a sequence, we just have a list of terms. But in a series, we have a list of terms, and then we're trying to add them all up. So I think, yeah, there's a nice illustration of that with this next problem, because we have this sequence here, 8n over 3n plus 2. The sequence converges. It converges to 8/3. Why is that? Well, because when n is really big, this plus 2 doesn't really matter, so I essentially have 8n over 3n, which is just 8/3. So the bigger n gets, the closer this fraction gets to 8/3. However, the series diverges because we're adding together. Well, here, let me write out what this means. The series, the sum from n equals 1 to infinity of an, which in this case is 8n over 3n plus 2. This means, let's see, let me plug in 1. I'll get 8 over 5 plus, and then when I plug in n equals 2, I get 16 over 8. Yeah, that's right, and that's just 2. And then when I plug in 3, I get 24 over 11. Plus, and when I plug in 4, I get 32 over 14. And I'm adding together a bunch of terms, but the farther you go, the closer and closer each term gets to 8/3. That's what we discussed here when we were talking about the series. So we're essentially adding together a bunch of things that look like 8/3. So when you add together 8/3 plus 8/3 plus 8/3 over and over again forever, that does not settle down at a single number. That's growing without bound. It's approaching infinity. So that series diverges. Okay, in the next question, 17, they give us a series with partial sums given by this formula. So the partial sums, remember, that's what you get when you just add some of these numbers up. So in this previous example, S1 is 8/5. S2 is 8/5 plus 2. S3 is 8/5 plus 2 plus 24/11. And so on. So evaluating the sum of the series is taking the limit of the partial sums. Let me write that out here. The sum of the series, sorry, that's cut off a little bit. It's 2 minus 3 times 0.8 to the n. The sum of the series means the same thing as the limit of the partial sums. And this limit does exist. When you multiply 0.8 with itself many times, what you get, the result gets smaller and smaller. So this term becomes insignificant when n is large, and overall the limit is just 2. This last question here is about a telescoping series. They're asking whether this converges or diverges. This looks scary, but if we just write out the first few terms, it's not so bad. So the first partial sum is just the first term, which is cosine of 1 over 1 minus cosine of 1 over 2. Okay, and if you really want to evaluate that, that's cosine of 1. Oh yeah, okay. I don't know what the cosine of 1 is. The second partial sum is a1 plus a2, which is the cosine of 1 over 1 minus the cosine of 1 over 2. And then a2 is the cosine of 1 over 2 minus the cosine of 1 over 3. And the cosine of 1 over 2 cancels, and we're left with just cosine of 1 over 1 minus cosine of 1/3. The pattern continues, so the nth partial sum, the sum of the first n terms, is going to end up being cosine of 1 over 1 minus the cosine of 1 over n plus 1. These n terms have 2n cosines being added and subtracted, but everything in the middle cancels out just like this did. All that's left is the cosine of 1 over 1 at the beginning and the minus cosine of 1 over n plus 1 at the end. And if we take the limit of this as n approaches infinity, we get the limit of cosine of 1 minus the cosine of 1 over n plus 1. N plus 1 is approaching infinity, so 1 over n plus 1 is approaching 0. So cosine of 1 over n plus 1 is approaching the cosine of 0. And if we like, I guess we could simplify that. Cosine of 0 is 1. So this series converges to cosine of 1 minus 1. All right, we have worked through all of the problems in this little review document. Are there questions about any of the problems here? Are there topics you'd like me to talk about a little bit more? Can I send the PDF of the review document? Yeah, if anyone wants this review document, send me an email and I'll reply with the document. I'm not sure if I'm meant to share this document with the whole course in an announcement, but if you send me an email, I'd be happy to reply with the PDF. How do you find the m and dm in the center of mass equations? Great question. Center of mass. So, the mass, I guess. I wasn't using the notation dm at the beginning when I did this problem, but that's what I was finding, is the mass of a little piece. And the way that you find the mass of that small piece there is you take its area and multiply by the density. We were just told that the density is some constant rho, and then the area of that rectangle is its width, which is dx, times its height, which is f of x. So I did the height, 1/2 x squared, times the width, dx. Together that makes the area, and I multiplied that by the density. That was dm. And then the way you find the total mass is you look at the masses of all the little pieces and you add them up. So capital M is the integral of dm. Could I talk a little bit about parametric curves but linear? Could you say a little more what you mean by that? Like, is there a particular problem you have in mind with these sort of linear parametric curves? A parametric curve. Oh yeah, given a linear function, how do you find a parametric curve? I see. Well, that's actually pretty easy, because if you have, I guess if you ever have the function y equals f of x, and it could be mx plus b, but it doesn't have to be. There's always an easy way to parameterize this, which is you can say x equals t. You can always say x equals t, and then y equals f of t. That is a way to parameterize any function at all, where it's y equals some function of x. That was not the case with things here. Y is not a function of x. You can see this fails the vertical line test pretty badly. So you couldn't parameterize this curve that way. But if you have y as a function of x, this works. Does that answer your question? Great. Any other questions before we wrap up? All right, let's call it a day then. Best of luck on the exam tomorrow. I hope you all have a fantastic spring break. I'll be continuing with the Monday night streams at 8 p.m. When we come back after break. I've got some really cool topics picked out. Series are a very hard topic, and in Calc 2 you don't always get to see some of the really cool things that you can do with series. My thought is if you have to suffer through learning how to work with series, you might as well get to see some of the really powerful things that they can do for you. So come back on Monday evenings at 8 p.m. after spring break. And for now, stick around for a minute. I've never rated someone on Twitch, but I'm going to send you all over to Matt Henningsen. He's a Denver Bronco, but he's streaming chess right now. So good luck on the exam. I'll see you after break, hopefully. Let's see. Here we go.